Okay, let's get going. I hope everything's going okay. The graded homeworks, we wanted to, there are some homework graded to hand back to you. Because it was going to be a bit chaotic if we tried to hand them out in class. What we're doing is they're in the kitchen right next to my lab. So the lab is where Darwin has the TA office hours. And then just outside of there, there's a kitchen. And so they're in there. If you want to go and get them, you can get them any time. Hopefully, we'll see how that goes. Hopefully that won't get too chaotic and it'll spread the load a little bit. Here's the outline of the class from the website. Right, this is where the plan anyway. And so we're now here, October 7th. We're supposed to be finishing off the Z-transform, but we were sort of like half a class behind, so we're sort of midway through the Z-transform. We'll see how that goes. That's this week. Then next week, and then we have the midterm coming up here. So that's coming up. And the plan for the midterm at the moment is just to have a regular class session, but instead of a lecture, you'll come in and do some questions during the time. As you see, it's stabilized quite nicely now, so the room is not too crowded. But there are still 100 students registered. So presumably we'll have a slightly higher turnout for the midterm, which will be kind of not ideal. But we can technically accommodate it, so that's the plan at the moment. I'm also going to be away, I think, both of these sessions. So we'll have to come up with some other plan for what to do on that Monday. I haven't figured out what to do yet, but I'll let you know what's happening there. Any questions about that stuff? Yeah.
Will you be posting any past exams?
Oh, thank you. Yes, I will be posting some past midterms for the past 2 years. I meant to do that this morning, so I'll do that when I get back to my office. You'll see the form of the questions. So they're different from the homework questions in that they're a little more tricky, right? I mean, they're just sort of, they're testing whether you can figure out the right kind of tools to apply, which isn't the form of the homework questions. But I'm trying hard to avoid it being a time test, right? That I'm not interested in finding out whether you're fast. I'm interested in finding out whether you understand the material. So I try and make it something that you can do without too much trouble in the allotted time. Although, of course, that's always a problem. That's always, because if you get on the wrong track, you can lose a lot of time. So there's always some pressure, but mostly I'm just trying to probe your level of understanding. Okay. So we started talking about the Z-transform. And here's the definition. The Z-transform is that G of Z is the summation of a sequence G of n over all values of n multiplied by Z to the minus n. And what this is doing is turning a sequence, G of n, into this function of Z, which is a complex variable. And one way of thinking about this is that it's we're defining a polynomial in Z, right? It's a set of discrete powers of Z. Each power of Z has a coefficient, which is a particular value of G of n, a value of the sequence at a particular time. A sequence is a set of discrete values. It may be one of unlimited length, but it's discrete. And so a polynomial is a function of a variable that's determined by a set of coefficients. And so here we're taking the coefficients of the value of the sequence. Now the polynomial may involve both positive and negative values of Z, and in general it may not have a finite order. But that's essentially what we're doing. And the idea, the weird part about that is we have a sequence which in many cases is a literal, explicit sequence with a set of actual values, not necessarily real values, but actual values. I mean, they could be complex. But we're converting it into a function of a variable, which is not so much a real value. It's a function. It's defined over a domain. But that's because it gives us a different perspective on the sequence. So we looked at this example here. So if x of n is our nice geometric or exponential sequence, in this case lambda to the n times mu of n, then, well, the z transform is defined as the sum over all x of n z to the minus n. So in this case, it's the sum from n equals 0 to infinity, because of the mu of n, times lambda to the n z to the minus n, which is our one-sided infinite geometric sum, whose closed form solution is this, 1 over 1 minus lambda z to the minus 1, provided this thing that we're raising to successively higher powers has a magnitude smaller than 1. So provided lambda z to the minus 1 is smaller than 1. So this is actually what the z transform is. That's the definition. Here we have a closed form expression that'll give us its value, but only for certain values of z, only for values of z that conform to this constraint. And this is, and so we tried to evaluate this. We actually tried to evaluate this expression, this, for some finite length g of n, which was an exponential sequence, and we did it in MATLAB, and we got something that looked like this. So here's my z-plane. These are, I guess, this is the imaginary axis. This is the real axis. So any point on this ground plane gives me some particular value of z with a real part and an imaginary part. I evaluated the sum of my sequence, which was a nice decaying exponential sequence, over 1,000 points, multiplying, raising some value of z to successively negative powers of n, summed them up, and then I just stored that in an array. So this looks like a continuous surface, but actually it's like every 0.01 or something. I got a complex value because the value of z is complex. But I take the magnitude of that so I can plot it, and I make this 3D plot, which is the magnitude of that g of z that I calculate as a function of z. And we see out here, it's nice and smooth and has this nice, interesting shape. And then there's this circular boundary where suddenly it just diverges, right? It goes out of control. And so we typically observe this with many z transforms, particularly for infinite length sequences. And so we call this range of values of z for which the value of g of z converges, we call it the region of convergence. And this range of values in here, where when we try and evaluate g of z, it blows up, that's not the region of convergence. That's the part that's not in the region of convergence. And we typically get this result where there's some circular value. We frequently get this situation where there's a circular value where the values do not converge. And so that gives us this concept of a region of convergence. And so it's typically we can draw it like this, that here's the whole z-plane. Now we're looking at that plot from above, and the shaded region is the values of z for which the sum converged, and then the blank values are the values of z where it didn't converge, and so they're the part that are not in the region of convergence. And this is the picture that we saw, right, that there was some circular region for values of z outside, larger than that circle, we were okay, and then for values of z inside, we were not. And that's exactly this case, right? So it's actually the constraint is on lambda divided by z needs to be smaller than 1. So as long as z is large enough, then that ratio will be small enough and we'll be okay. So this thing here, this closed form solution, we're almost always going to call this the z transform. But the right way to think about it, I think, is it's a closed form expression that gives us the value of the z transform within the region of convergence, which is a different thing, right? Within the region of convergence, it's equal. But it's not equal unconditionally. It's only in that region of convergence. And so, the way I was taught this, or the way that I absorbed it when I was taught it, was this is the Z transform, and then there's this thing called region of convergence, which you have to sort of drag along with it, which is somehow part of it. But no, this is the Z transform, which includes, these values which are unbounded, which are ill-defined. This is a closed form expression which gives us the value of the Z transform, but only over some range of values, which is why we have the region of convergence. And that to me is more satisfying. I'm not sure if, I don't know. I'm sort of stressing this, I'm laboring this because it was a big insight for me to sort of think about it this other way around. But maybe that's not a problem you've encountered. So because here's the tricks we play, right? So now it's like, here's a different sequence, and this is a left-sided sequence, so it's 0 for all values of n greater than some number, which is 0 in this case, and it's non-zero for these negative values. So if we define it as, so mu of minus n minus 1 is this left-sided step function. And then it's minus lambda to the n times that. So it's like, here's my lambda to the n. In this case, well, here's my lambda to the minus n. Sorry, here's my lambda to the n for negative n, right? And then if lambda has a magnitude smaller than 1, then raising it to successively negative powers will give me this diverging shape like this. And then it's the negative of that. So this is like if lambda was 0.9 or 0.8 or something, then minus lambda to the minus n would be minus 1 on 0.8, minus 1 on 0.64, etc. And so it would look like this. Now, if you plug that into the Z transform here, here's my x of n, here's my z to the minus n. I can take this mu of minus n minus 1. It's not obvious that it's not totally obvious that's a left-sided step function, but if you evaluate it for different values of n, you'll see that it works. So that gives us, that's only non-zero for n less than 0, so n equal minus infinity to minus 1. And then we take the minus sign out here, so we get minus sum over this range, lambda to the n, z to the minus n, which is, we can do a change of variable here, so we can say m equal minus n. And so it's the sum from m equal 1 to infinity of lambda to the minus n, z to the m, which now we can recognize as something we can solve with our geometric series identity, provided this thing has a magnitude smaller than 1. So provided z divided by lambda has a magnitude smaller than 1, which means that the magnitude of lambda is greater than the magnitude of z. In that case, it works out to be this. We get that out. It's starting from power 1, so we get one of these on the top. And then if we just multiply that through top and bottom, we get this coming out. Now, why did we start with this one? Because this is the same closed form expression as we had for the other sequence, right? If we go back to here, the closed form expression we get is 1 over 1 minus lambda z to minus 1 for this sequence here. It's a different, this is a different lambda I've drawn it for. For the same lambda, it would be a decaying sequence here. Here we get 1 over 1 minus lambda z to minus 1, same sequence. But it's a different region of convergence, right? Here, the region of convergence has an upper bound at lambda. So it's the values within a circle. So here I've sort of contrasted these two cases. X of n equal to lambda n mu of n, which is the case we had. X of z is 1 over 1 minus lambda z for magnitude of z greater than lambda. And then, so it's this region out here. Within this circle, x of z blows up. It's the big, infinite column. Here's a different x of n, minus lambda to the n mu of minus n minus 1. So it's this left-sided sequence. When we work it through, x of z is 1 over 1 minus lambda z to the minus 1. But the region of convergence is now z smaller than lambda. It's this region in here, right? And then if we try to actually evaluate it for values of z outside of here, it would again blow up, right? So now it's the complement of that picture that we saw in MATLAB. Now it just happens that the closed form expression for the values of z within the regions of convergence of these two sequences. It's the same closed form expression, but of course there's no value of z for which both of these regions of convergence is valid. And so they're different sequences with different z transforms, right? Because the z transform is the actual value of g of z for some set of values of z. But it happens they have the same closed form expression because the closed form expression is valid over different ranges of values of z. And so this is like possibly the most confusing way of presenting it, because it's like, wait, you're saying the z transform is the same, but the sequences are different. No, this is just kind of a way of revealing why this is a tricky and confusing thing. The z transforms are completely different because z transform completely defines a sequence. These sequences are completely different. But the way we handle z transforms, which is in terms of using these closed form expressions, just happens these things work out the same. And the reason that doesn't mean the sequence is the same is because they're applying to different regions.
At what point in the derivation do you come up with the region of convergence?
Where in the derivation does the region of convergence come in? It's here. Well, the way we're doing it is always when we apply this this geometric series identity, right? So this is still there's nothing. We haven't done anything weird here. This is just true. This is just algebra. But to go from there to here requires using this geometric series identity, which is, the 1 minus cs equals something, and then you divide through by the 1 minus c. Right? Remember? Yeah, okay. But that relies on the fact that the geometric series, as you go to infinity, this term disappears. And so that relies on this thing having a magnitude that's smaller than 1. So when we raise it to higher and higher powers, it just disappears. And that's what gives us the constraint. Basically saying that lambda, in this case, lambda to the minus 1z has to have magnitude smaller than 1. So magnitude of z has to be smaller than magnitude of lambda. So it all works out. It's nothing. It's not. It's. If you remember where it's coming from, it all makes sense. But of course, you don't normally want to think about this level of detail when you're thinking about it. So we just have this. We have this thing about regions of convergence, which is easy to get right, as we'll see. Yeah.
If you're given a C transform of some certain function, how will I know that it is from, for example, a causal sequence or
Yes.
a causal sequence?
That's great. So if someone gives you a z transform like this and says, oh, so what sequence does this correspond to? It's like, wait, you told me what the closed form expression was for this z transform, but you didn't tell me which values it was valid for, which values z. It's not a well-formed question, right? It's like, I have a z transform, and over some regions, some values of z, I can tell you what its values are, but I'm not telling you which values it is. Well, it turns out that it can't be for all values of z, because there's a value of z where this thing goes to infinity, which is bad. I can't think of a better explanation than that. But we're going to say that the z transform can't go to infinity. And so here, when this thing goes to 1, then this becomes 1 over 0. And so we definitely want to avoid that. So this is not. Anyway, it just happens that there is no sequence for which this is true for all values of z. It's only going to apply for some limited region of convergence. And so, in general, if someone tells you the closed form expression but doesn't tell you the region of convergence, then you don't know the answer, right? Because in this case, clearly it could be either of these two, right? If someone tells you it's this but doesn't specify the region of convergence, then it could be these two sequences. Turns out these are the only two sequences it could be. So there are only two possible regions of convergence we have to worry about here. But without saying which part of the surface it is, you haven't really specified it, because it isn't both. Yeah?
On the next slide, when you go from the summation into the fraction, there's a multiplier in front.
Which slide? The one after this?
The one, yes.
This one? No.
Sorry, before.
Okay.
So the negative lambda to the negative 1c, does that just come from the s minus s times c?
Yes.
Way of evaluating?
Right. So where does this thing come from? This is the geometric sum. There's a negative. I don't know. I think it's right. This is a geometric sum from m equal 1 to infinity The identity is typically written from m equals 0 to infinity. And so you could say, or you could divide out one term here, and then it would become from 0 to infinity, right? And so that's this term here, and then this is the identity for 0 to infinity. But then when you multiply it through, this is z divided by, it does work. This is z divided by lambda, so you get z on z divided by lambda. It works. I'm sure it works, right?
So if it were from m equal 5, for example?
Yes.
So
right.
I think, can you just do lambda to the negative 5z to the 5th times?
So if we had some other mu function in here, which would basically be, it's not exact. If we change the mu function, it would be like changing the mask, the values that were non-zero here. But we could get something very similar just by shifting this whole thing in time, right? Then we get a similar expression in here. Shifting it in time, as we're about to see, is the z transform of a function that's shifted in time is just z to the minus n0 times that function. So if we just put a z, some constant power of z on top of here, we get the z transform of a sequence that's shifted. And then you can see that's going to work out here. But yeah, we get different powers of z out here, and then it wouldn't be quite so neat. But yeah, it would look the same. Yeah?
So because they have two different regions of convergence, do they have the same range of values between the two?
So if they have two regions of convergence, they have the same values. I think not. I think, so this picture, this MATLAB picture, right, that's one of the regions. That's the value of g of z for the right-sided sequence, x of z, magnitude of x of z. And then this expression, right, this doesn't work so well. This closed form expression x of z here, we can plot that. That was the other part of the MATLAB demo, and it's actually this. This is just the magnitude of 1 over 1 minus lambda z to the minus 1 for all values of z. And so if you look at this, if you compare these two, I'm just going to alternate between them. You see, this is the actual z transform, but it's the same as the closed form expression, within the region of convergence out here. It's just that outside of the region of convergence, the inner circle, 1 over 1 minus lambda z to the minus 1 continues to have a nice, continuous, well-behaved function, but the z transform blows up. And so the other function, which I haven't plotted, would be this interior part and then blowing up everywhere outside. So you see the two g of z's, g of z and h of z, or g1 of z and g2 of z, have different values. They have different values actually for every value of z. But it just happens that the convergent values are about one another at the boundary, which is this z equal lambda radius. Yeah?
Sorry, this is the plot for the sum of the two sequences, or just the end?
No, this is the plot for the closed form expression, which is not the z transform of anything, right? Because if we sum the two sequences, so the z transform is linear. If you take two sequences and you add them up, then the z transform is the sum of two z transforms. But if we have values which are divergent, which are effectively infinity, then if we sum them up, you don't get the nice part, you get the nasty part, right? Okay, so that's great. Another question.
Basically, when I say Z transform, basically rose up outside the region of convergence.
Yes.
How do you basically visualize it in terms of maybe the frequency response of signal, or essentially it's everything is a frequency term, right? So if you say for a few values of Z, it basically is infinite. How do you basically visualize it?
So the question is, how do you visualize or relate the z transforms, the frequency response, and stuff like this? That's the whole point. So that's what we're going to spend the rest of the time talking about. I mean, the rest of this week and next week. Okay. So just let me know if I don't answer that. But so here's the point. A single G of Z closed form expression can match multiple sequences depending on which region of convergence you specify. That's what this has shown, and I think we've sort of gotten the idea now. And so by extension, if someone is trying to define a Z transform, they can say, I've got the Z transform, I've got this nice closed form expression for its values, but they need to specify for which values of Z it's valid, else they haven't given you enough information to actually work out to figure out what the Z transform is. And that's a classic way of taking points off people in a test. If you're asked to take Z transform of a function and you don't specify the region of convergence, then you haven't fully done your job. Okay. So these Z transform expressions are, it's the ability that we can work out these closed form expressions obviously makes this whole thing useful. If we had this, we could define a Z transform, and it's like, well, you can evaluate its value, but it's like this long, infinite sum or something like that. That wouldn't be very handy. But it turns out that very often we can get these closed form expressions for the values of the Z transform within the region of convergence that work out to be these polynomials, or in particular rational polynomials in Z, which then are things we can handle and things that have nice, well-behaved properties. So in general, G of Z could be anything, but the kinds of signals and systems we're going to deal with are going to be these ones that have rational polynomial Z transforms. You see there I'm doing it. I'm calling it the Z transform, but it's actually the rational polynomial closed form expression for Z transform within the region of convergence, which is a mouthful. So we say rational polynomial Z transforms, which means they're like this. So the G of Z, I can write it as P of Z divided by D of Z, where P of Z and D of Z are finite order polynomials in Z. We said that G of Z could be regarded as a polynomial in Z, but it's like infinite order in general. But if we have it as interestingly, the ratio of two polynomials like this, you can expand it out as a single polynomial, but it's infinite order, but you can describe it with these two finite order polynomials. Obviously, when it's ratios like this, you can multiply top and bottom by Z to the K or something, and get different equivalent forms. But here, by convention, we have the highest order of Z, BZ to the 0, and then all the other powers of Z are negative, because that kind of reminds us of the use of negative Z's in the Z transform, or maybe some deeper reason. We note here we're using P's and D's with finite subscripts, which is similar to the variables we used in the LCCDE expression, and that's not a coincidence. It turns out they're the same values, as we'll see in a little bit. If we have a G of Z written this way as the ratio of two polynomials in Z, if we have a polynomial in Z, we can factor it. We can find some set of terms here such that that polynomial we had before, the successively more negative powers of Z with different coefficients, works out as the product of a set of terms like this, 1 minus zeta L to Z minus 1 for L equals 1 to M, and then some constant out front. Right, you can always factor a polynomial like this. And the zeta L's are then the values where the polynomial evaluates to 0, so they're the roots. So we can do this both numerator and denominator. We end up with a set of coefficients here. We get these are not terribly interesting coefficients. These are just a constant scaling term. These are interesting coefficients. The zetas are the values where the numerator is 0, which means the entire thing, G of Z, becomes 0. And they are called the zeros of the function of Z, G of Z. They're called the zeros of the Z transform. But they're really a property of the closed form expression for Z transform. And then these lambdas are the values where the denominator becomes 0, which means that the whole expression, the ratio, goes off to infinity, and they're called the poles of G of Z. the values at which the closed form expression goes to infinity. The interesting thing is that, so poles and zeros are basically, if someone tells you, oh, here are my zeros, here are my poles, you can plug them back into this expression, you can work out the entire polynomial. So a rational polynomial like this is fully specified by its poles and zeros and a constant term, which is, less interesting. So knowing the poles and zeros is basically everything you need to know about this closed form expression. If the closed form expression is telling us the values of the Z transform, then that's great, because we might care about those. We haven't fully described why, but they're probably something we care about. It may be that the poles and zeros aren't in the region of convergence, aren't actually values of Z where this closed form expression matches our Z transform, but they still determine its behavior, right? Now all we care about is the overall shape of this closed form expression, which is determined by all the poles and zeros, even if they're not in the immediate vicinity. And so this is how we sort of end up forgetting about the region of convergence, because now we're just interested in this closed form expression, and it's easier to think about those over their entire surface. Okay, so if we've got, so that was kind of like, I'm still trying to inoculate you against this confusion between the closed form and the actual Z transform, but probably we shouldn't worry about it too much. So we've got this closed form expression in terms of a rational polynomial, which has a bunch of poles and zeros, roots to its numerator and denominator. And so we can simply plot those on the Z-plane. So here we can plot, the ground plane of that surface. The real Z is a complex variable with any possible complex values. So here's the real parts, the imaginary parts. And then there was a set of specific values of Z where the numerator took on the values of 0, and so we can plot those. And by convention, we plot them with little circles, little O's. And then there are the set of values where the denominator took on the value of 0, so the whole function kind of blew up. And we call them the poles, and by convention we plot those as little x's on this Cartesian complex Z-plane. And then, like I say, if someone gives you a picture like this with a set of roots, and you can tell which ones are the roots of the numerator and which ones are the roots of the denominator, you can basically read them off. You can reconstruct the polynomial, so you can reconstruct the entire function for all values of Z just by knowing where these roots are, if you know it's a rational polynomial function. So that means that just given the roots, you can work out the value of the expression for any other value of Z up to a scaling factor. And so that's what we can do here. This function, right, that I showed you in MATLAB, this was what I did here, what I actually did, right, in the MATLAB script. Was here, right? I just ran through all these possible values of Z, and I just filled in, here's the closed form expression, I just evaluated it and wrote it in, and then I'm just, to plot that surface, I'm just plotting the absolute value of this, and I just chopped it off if it gets too large. So it's just plotting that value, but it has this nice behavior. And what we see here is that there's this thing sticking up here, looks kind of like a tent with a tent pole in it. That's the pole, right? This expression, 1 over 1 minus lambda z to the minus 1, has the denominator goes to 0 when z equal lambda. So this is a root of the denominator, so it's a pole where the magnitude of x of z goes to, magnitude of that closed form expression goes to infinity. There's a 0 here. It turns out that when z is 0, that whole thing goes to 0. So that's kind of like a not very interesting 0, because you can... The zeros at the origin at z equals 0 are not as interesting as the zeros elsewhere. Let's put it like that. So that's for a simple function with just a single pole and a single 0. For this, right, this is taking this function here. Well, I don't know if it is actually that function. Taking a more complex function here with 2 poles here and 2 zeros here and here. And then you see Again, we have two of these places where the value of x of z goes to infinity, and then two places where the value goes to 0. Here I'm plotting the log of the magnitude. So actually going to 0, the log is negative infinity, so it's sort of symmetric in the poles sticking up, and then there are like deep sinkholes sticking down over the zeros. But we get this entire surface. And then this is what I'm saying about, if you know, this is how it sort of works. If you know the position of these poles, then they sort of have this influence, right? They basically have this 1 over radius effect on the magnitude. And so you can sort of see how the shape, the value of the surface at all points on the surface is determined by the relative influence of all these poles and zeros. And that's the only thing that's influencing it. Now, your question earlier was, well, how does this, what are these values? How do we visualize this, and what does this relate to the frequency response, the Fourier transform? So here's the point. We said that g of z, the way we defined it, it looked just like the dTft, except that instead of having e to the j omega, we had z to the minus 1. So that means if we evaluate g of z for z equal e to the j omega, we get the Fourier transform, which is the amount of the different frequency components, different sinusoids. Z equal e to the j omega is just a unit length vector with angle omega on the z plane. And so we can plot this circle here, which is the unit circle, and it's the set of z such that z equal e to the j omega for all omega. And then we can find out what the values of g of z are for those values of z, and that gives us this sort of, this is the intersection between some circular cylinder and this surface here, but these are the actual values of the dTft. So if we have this set of values here, which is the intersection between those two, we can now unwrap this and plot it as a function of omega. So if I plot it from 0 through to pi, I get this. So this is the 0th value here. It goes up, here's this peak, goes round, it goes down, and here's this trough. And this is just the magnitude of g of e to j omega, the dTft. And in this particular case, this system, this sequence, or could be a system, has this kind of set of frequencies where it's got large gain, and a set of frequencies where it has less energy, less gain, however you want to think about it. And so it's like, okay, that's interesting, that's a nice frequency response, but, we just have to work it out, look at it, and then figure it out. But when we look at it from here, it's like, oh, these large values here are coming because we're slicing through the slope around this pole. And so now, this is the whole payoff. That knowing where the poles are, and knowing where they are in relation to the unit circle, the poles and the zeros, right? This dip here is because we're approaching this 0 down here. We know where the poles and zeros are. We can sort of guess how they're going to interact with the unit circle. That will then tell us what the Fourier transform is going to look like, and then we quickly get an insight or a rough idea about what the system is going to do. And that's the real power of thinking about discrete time systems and signals in this Z-transform domain, that suddenly the features of the Fourier transform, which is very, very concrete, right? It's how much certain frequency components are present or are going to be, how they're going to be treated. These features then relate to these fundamental properties, the roots of the Z-transform closed form expression, and they relate in a very simple and intuitive way that poles tend to lift it up and zeros tend to push it down. So that's the point, and we're gonna continue to pursue that for a bit. Yeah.
So basically, this correlation between Z transform and the FT. So this is basically done only in the region of conversions.
Right. So that's a good point. Thank you. So here, see what I've done here. I've plotted the x of z, the closed form expression for all values of z, and the region of convergence has been forgotten. Right? I've just said there's no actual sequence that has a Z transform that can take on this form. I've stated that. I haven't proved it, but it's true. This was the Z transform of some sequence, and it had a region of convergence which meant that it was the true values for some set of values of z, and there was other values where it didn't work. Now, I started talking about the Fourier transform as like, oh, and that's the values of x of z for z of unit radius. The x of z I'm talking about there is not the closed form expression, it's the actual z transform, meaning I have to think about the region of convergence. And so here I want to take x of z for z equals e to j omega. I want that to be the actual values of x of z. This is only going to work if my unit circle is in my region of convergence. So here, because otherwise when I actually evaluate x of z, I just get these blown up values, right? So this relies on the idea that the unit circle is within the region of convergence. We'll talk about that more in a second, but thank you for pointing that out. Yeah?
Why is it that you're looking at values exactly at the unit circle to evaluate the DTFT?
The reason we're looking just at the values on the unit circle is because the DTFT, x of, the DTFT is x of e to j omega equals the sum over all n of x of n e to the minus j omega n, right? And the z transform, x of z, is equal to the sum over all n of x of n z to the minus n, which is equal to DTFT. Well, if z is equal to e to the j omega, it's equal to DTFT, right? So that's what we're saying, that by evaluating the z transform for this particular set of values of z, which is the unit circle, right? Because this thing has a magnitude of 1 and a radius of omega, an angle of omega. So for this particular, this is a function over all possible values of a complex value. So it's all possible values on a Cartesian plane. But there's a subset of these, a one-dimensional subset, a circle in this case. And when we evaluate those, we just get this thing. And of course, it even works algebraically, because here this expression had e to the j omega where we put the z. And so it's just saying, well, yeah, if it turns out that if we just think of z being this constrained set of values e to the j omega, this is what we get. Okay. So that's kind of the point. And now let's just look through some of the properties of the z transform just so that we can work with it and see what's going on. It's linear, which means that if we have two sequences and we add them, then we can add the z transforms. And it's sort of, because there's nothing particularly exotic going on here. It's not surprising that it's linear. It's easy to prove this just by doing our thing of expressing one sequence as a linear sum of two other sequences, putting it through the z transform, rearranging it so we get the z transforms of the two original sequences coming out, and then showing that, yes, it's the same linear combination that comes out. And this point about convergence, right? So, well, this, again, there's nothing, convergence is not that exotic. It's literally, if it's not converging, it's going to blow up. If we add together two sequences, if either of them blows up, then the sum is going to blow up. So the region of convergence has to be the intersection of the two regions of convergence or intersection of the regions of convergence of the sequences that we're summing up. And so, for instance, if we have two right-sided exponential sequences like this, lambda 1 to the n, lambda 2 to the n, maybe with some scaling functions here, both multiplied by mu of n, then linearity says, well, we can just calculate z transform each of these sequences individually. This one is just alpha 1 on 1 minus lambda 1 z to the minus 1. This is alpha 2 on 1 minus lambda 2 z to the minus 1. But to do each of these, we had to do that whole thing with the geometric sequence. So we had to have this thing have a magnitude smaller than 1. So in this case, well, lambda has to be larger than, z has to be larger than lambda 1. In this case, z has to be larger than lambda 2. So z has to be, both of those things has to be larger than both of these, which means it has to be larger than the larger of them. for it to work. That's the intersection of the region of convergence. Okay, so we've got this Z transform. It's something that seems like it's going to be a quick way to understand something about the Fourier transform, the behavior in the frequency domain. We've got systems that we can build easily, which are systems defined by these linear constant coefficient difference equations. So systems where we basically just have delays, gains, and then feed forward or feed back. With a finite number of delays, we can express them in terms of these LCCDEs. The LCCDEs, we could, the outputs of those systems, like things like the impulse response, we had this whole closed form expression. They had this kind of form. They had the lambda, which was the root of the characteristic polynomial. Each of those would have we'd have a sequence with that base, some scaling factor, which are the things we solved for using the initial conditions. And then it was assumed to be right-sided. It was assumed to be from some time going onwards. If we have an expression like this, with a bunch of terms like that, well, what we just saw was each of these terms, its Z transform becomes something like this. And so we can have the Z transform of at least the complementary solution of some LCCDE expression. We've got it already. It's a set of terms like this. And moreover, these are now going to be, the poles of our, well, no, I haven't shown that yet. But it's going to be some kind of expression which will be a nice, closed form expression with a few terms like this, one for each of the roots of the complementary solution. And it's going to have a region of convergence, which is basically going to be the intersection of each of those. So it's going to be the least, the region of convergence that's most difficult to achieve. So it's going to be the region of convergence with the largest region of non-convergence. But it's always going to be, for a right-sided sequence like this, it's always going to be the outside of some area like this. And so it's going to be the outside of the largest circle. The actual circles are at radius lambda, or radius of the magnitude of lambda. So it's going to be the outside of the largest lambda of all the lambda terms, all the roots of the characteristic polynomial. Because there's nothing particularly weird going on there because of the way that Z shows up in the Z transform. If you're taking successively higher powers, if you've got a right-sided sequence, that means you're raising Z to the negative something larger. So you want so if Z you want a large Z, because then when you raise it to negative some high power, it gets very, very small, 1 over Z to the n. And so then it's only when Z gets smaller that you get problems with the convergence. And so that's why the small values of Z, the values of Z with small magnitudes are the ones that cause it to blow up. And so the region of convergence is always the outside of some circle for right-sided sequences. Okay, let's just look at this. Now I'm thinking that sequencing of these slides isn't as good as it could be. But let's just look at this again to just sort of cement this idea. Let's look at this quickly. This idea of sidedness and regions of convergence and different sequences having possibly the same closed form, but closed form expression that applies over different regions. So we saw before that if we have g of z of 1 over 1 minus lambda z, 1 over 1 minus lambda z to minus 1, for a value of lambda like 0.8, we could have this would be the closed form expression for this expression here, lambda the n mu of n, but it would have this region of convergence which is the outside of the circle, like it was this could be the solution to some LCCDE, right? It's going to be the inside. And then we saw that if it was negative lambda the n mu to the minus n, mu of minus n to minus 1, mu of minus n minus 1, it was like this. So this is now the same value of lambda. If lambda was smaller than 1, giving something like this, then the negative of it is like, as you raise it to negative powers, it diverges like this. And that's got this region of convergence, which is now the inside of some circle. And the the G of Z closed form happens to be the same. So we could have these two sequences, and and we can do linear combinations of them, and we get linear combinations of the Z transforms with different regions of convergence. And the regional convergence are the intersections of each of those. So this is a setup for this idea here. Well, let's say we've got a system here with an expression here with two of these terms with different values of lambda. And let's say that we're thinking about a value of lambda 1, which is smaller than 1, lambda 2 greater than 1, just so that we can see them separately. Well, based on this previous slide, each of these terms could correspond to two different sequences with different regions of convergence. So we haven't specified the region of convergence for this. So until we specify it, there's some ambiguity here. So this first term, lambda 1, could correspond to this left-sided sequence, which means the region of convergence is the inside of some circle, or this right-sided sequence, which would be the region of convergence outside a circle. And the same for lambda 2. Because lambda 1 is smaller than 1, it's this case where the right-sided sequence is convergent, left-sided is divergent. Lambda 2 is larger than 1, so the right-sided sequence is diverging, and actually then the left-sided sequence, raising lambda 2 to successively negative powers, would be converging and nice and well behaved like that. We could take one of these two and one of these two, and we could add them together, and we'd get a sequence with the same G of Z, but the only thing that would differentiate them would be the regions of convergence, which would be the intersection. So let's just look at all four of these, and we'll do them one by one. So case 1, we have G of n is equal to lambda 1 to the n mu of n plus lambda 2 to the n mu of n. So there's two right-sided sequences, one of which is converging, one of which is diverging. When we take the Z transform, we'll find this, but because they're both right-sided, we need both of these terms here to be smaller than 1, magnitude smaller than 1, which means that Z has to be larger than lambda 1 and larger than lambda 2. So here are two circles, lambda 1 and lambda 2, and we're saying, well, it has to be larger than both of these, which means it has to be larger than the larger of these, which means the region of convergence is the exterior of this larger circle. And so here are the values of G of Z where it converges. And here's this, we've actually got poles here at lambda 1 and lambda 2. So here it is coming up to the edge of this pole, although technically it doesn't actually reach the value of the pole. It's strictly greater than lambda 2, so it never touches the pole, which is at lambda 2. But here's the surface, and then inside of here, inside this, where it's not plotted, it's basically diverging or infinite. So that's fine. We've got a sequence here. The sequence is not bounded, right? The values get larger as you go on, which means that we'd have a lot of trouble taking its Fourier transform. We said the Fourier transform was evaluating G of Z on the unit circle. This solid line here, we notice that the solid line is not within the region of convergence. That is, G of eta j omega is going to be one of these nasty divergent infinite values. And so that's sort of saying the same thing, that this kind of sequence is not something we like to deal with in discrete time because it's not bounded. The Fourier transform method is not going to work for us. And that's the same as just saying, well, yeah, you have a closed form expression for G of Z, but it's not valid on the G of eta j omega values that you care about. So that's sort of how that all plays out. So that was one of the sequences we could look at. Here's another one, but the two left-sided sequences, G of n is equal to minus lambda 1 to the n mu of minus n minus 1, minus lambda 2 to the n mu of minus n minus 1. So it's these two left-sided sequences. Again, one is converging, one is diverging, although it's the orange one that's converging here and the brown one that's diverging, or it's the other way around when it was right-sided. When we try and work this out, remember to solve this, we did this change of variable where we replaced m with minus n, and so we ended up actually wanting the reciprocal of this to be smaller than 1. So then it's actually we need Z to be smaller than lambda rather than larger than lambda, which means that we need it to be the interior of both of these circles, which now is the interior of the smaller circle. So this sequence, we can calculate Z transform. It has some region of convergence, which is now the inside of the circle. Here are the values of G of Z, where it's finite, and then for where it's not plotted, it's some divergent infinite value. We notice, so this is a shaded region here, we notice again, the unit circle is not it's not within the set of values of Z where the closed form expression is valid. And again, it's a sequence with unbounded values. And so, yeah, we're not going to be able to calculate a Fourier transform with this because there is no closed form expression for what the values of G of Z would be for Z equal to j omega. Here's a third way we could build this sequence. So now we're taking the right-sided version for lambda 1 and the left-sided version for lambda 2. And so now we've got these two convergent sequences, but they're going in opposite directions. So it's non-zero for all values of n, but it is bounded. And so in that case, we end up with different regions of convergence. We need Z to be larger than lambda 1. We need Z to be, which is the right-sided part. We need Z to be smaller than lambda 2, which is the left-sided part. That's okay, because there is a set of values of Z where that's true. It's the space between lambda 1 and lambda 2. It's this ring of values here. And so again, we've plotted the entire Z transform magnitude here for all values of Z, but where it's not visible, it's because it was divergent. But there's just a set of values of Z over this discrete range of, this fixed range of magnitudes where the sum converges. But now we notice that the unit circle is in the region of convergence, and this is a signal with bounded magnitude, something we can calculate its Fourier transform, and we can evaluate G of Z for Z equal to j omega. Just for completeness, here's the fourth way of building a sequence out of those two choices, the two divergent parts. In this case, we want the region of convergence constraint would be that Z must be smaller than lambda 1, larger than lambda 2, but lambda 1 is already smaller than lambda 2. So there's actually no values of Z where both of our constraints can be met. So on the face of it, you might think you could write down the Z transform like this, but then when you try and figure out the region of convergence, it's like, well, there is actually nowhere where this is valid. And so in sense, this doesn't really have any use, right? It's like it's some mathematical intermediate thing, but it doesn't actually tell us the value of G of Z anywhere, so it's kind of irrelevant. And so we said that Z transform can describe sequences that we can't describe, that we are unable to describe the Fourier transform. But here's a sequence where we're unable to describe it with a Z transform because there's no value of Z for which it converges. So, this is exploding in multiple ways. What they're saying is there's no value of R to the n x of n, G of n, which is convergent, and so we basically can't handle it with Z transform. But you see how it kind of emerged out of the way we're thinking about it. So that's kind of, it's just a little investigation of what this region of convergence and sidedness thing, how it works out. But there are a few things that come out of that. If we'd had lambda 1 equal to lambda 2, then a couple of sequences would have involved actually a complete exponential sequence. So it's like this is lambda to the n without a mu of n. So just g of n. So g of n is equal to alpha to the n, which would sort of be a right-sided sequence and a left-sided sequence. In this case, we could get the Z transform. This one would be 1 over 1 minus lambda to the n. Alpha to the n, this will be minus 1 over 1 minus alpha to the 1 minus alpha z to the minus 1. The region of convergence, this one would be, it's right-sided, so it would be outside of the alpha radius circle. This one would be the inside of the alpha radius circle. But because these relations are strictly greater than, strictly less than, again, we'd be in a situation where there is actually no set of points where both of these things converge. The Z transforms both of these converge. And so we wouldn't have any actual region of convergence. So this thing, even though it's something which is clearly the boundary case, you could actually make it bounded by multiplying it by alpha to the minus n. You still can't calculate Z transform because it's infinite length but constant value, so it doesn't converge for any value of Z. So a two-sided exponential does not have a convergent Z transform. Z transform does not exist, we say. Okay, so let's. I felt like we were really on a track to sort of get some sense of the Z transform here, and then I threw in all these things about regions of convergence again, and I feel like that was taking us away from stuff that makes sense. But so this is where we're getting up to, thinking about these LCCDEs and how they have regions of convergence which are well behaved but come from the roots of the LCCDE. Let's just work through that. We'll come back to that. So let's just work through some sequences and the Z transforms just to make sure that we know these things. We have some identities to hand. So this is like, here's the time domain sequence, here's the Z transform, and then obviously this is the closed form expression for Z transform values, and this is the region of convergence over which that closed form expression is valid, meaning that outside of that, for other values, it's non-convergent or infinite. If G of n is D of n, we just apply the sum of G of n, Z to the minus n. It's only non-zero for n equals 0, so it's Z to the 0, which is always 1, and so that actually converges for all values of Z. And that's nice because we know that the DTFT of that is 1, and so happily when we intersect this function which is 1 for all values of Z, when we intersect it with the unit cylinder, we get the DTFT equal to 1 as we hope it's going to be, as we expect it to be. Mu of n, the step sequence, remember we actually had a value for the DTFT of that, but when I put it up I said I don't know how it's derived, and it had some funny features. It had something funny going on because of course mu of n is not a finite energy sequence. It's, the further you go, you get more magnitude coming in. The Z transform, no problem. It's just 1 over 1 minus Z to the minus 1, because it's just a generalization of this, right? The Z transform we saw of alpha to the n, mu of n is just 1 over 1 minus alpha Z for values of Z larger than alpha. If we make alpha equal to 1, we get this, mu of n, and so it's this function, but just for the region magnitude of Z greater than 1. So again, we notice actually this does not include the unit circle, which is magnitude of Z equal to 1. So here we're saying the step function doesn't really have a DTFT, and so that thing I gave you before, I don't know, shouldn't exist. Which, I'm sorry that doesn't make any sense. I could have just said it doesn't exist, but there is a value for it. I don't know where it comes from. Doesn't matter. Okay, here's another sequence. Cosine omega n, so it's a cosine with frequency omega 0. Sorry, cosine omega 0 n, times r to the n. So let's generalize a little bit. We can actually put an exponential envelope on this times mu of n, so it's right-sided. We can build this out of a couple of alpha to the m mu of n's for alpha equal r e to the j omega 0 and r e to the minus j omega 0, right? Two conjugate complex exponentials. We sum them together. We can sum them together in time domain to get this. We can sum together Z transforms to get this, and we can do some rearrangement. So this is the cosine form and the sine form. They have the same denominators, which is a second-order polynomial in Z. And then it has these particular coefficients, minus 2r cosine omega and r squared. And if you factor that, you actually get two roots. They're complex conjugate roots, and they are, which are the poles of these closed form expressions. And they're actually the roots occur at r e to the j plus or minus omega 0. right? If you actually work that through, if you had a system, if you try and find the values for which this system, this expression, the values of z for which this expression is 0, they're these values here, z equal r e to the plus or minus j omega 0. So you have this conjugate pole pair corresponding to these sinusoidal components, and the sinusoidal components are at omega 0, and the poles are at angle omega 0, and then they've got this decay factor of r to the n, so it's just an exponential decay, and that's the radius here of these poles. And the difference between the cosine phase and the sine phase is just this first order polynomial in z on the top. And of course, I don't know. Yes, because we built these out of these two alpha to the n's, with alpha equal to this. So the region of convergence is z larger than the magnitude of the alpha, which in this case is r. And so we have the regions of convergence being we have these poles, and there's everything outside of the radius of the poles. Again, we'll come back to that. We'll see more of that. Some general properties here of the z-transform. These mirror the things that we had for the DTFT, and in fact, they have to be consistent with the DTFT. In each of these cases, if we substitute z equal e to the j omega, it should give us the corresponding expression for the DTFT. So if we conjugate the sequence in time, we conjugate it in the z-domain, but we also conjugate the z-plane, which means that we flip the imaginary axis. So if we have a z-plane like this, with this imaginary, then we take all the values and we mirror them in the real axis, and then we also conjugate them as well, and that would give us the entire z-transform surface for the conjugated time sequence. And the region of convergence, because the region of convergence is always bounded by circular boundaries on the z-plane. When you conjugate them, they're the same region, so the region of convergence stays the same. If you time reverse, then if you just put that into the z-transform expression, that's basically just flipping the order of powers of z. And so the z-transform of g of minus n is g of z to the minus 1 if g of z was the z-transform of g of n, or g of 1 over z. And if you can think about that as a transformation of the entire z-plane. For any point z, I can figure out where 1 over z would be. If z is a complex value, r e to the j theta, then 1 over z is 1 over r e to the j minus theta. So it's basically you take a point, you reflect it in the unit circle, right? Its radius becomes the reciprocal radius, and you also conjugate it. You reflect it in the real axis. And it's kind of a strange thing, that reciprocation of a complex value, but it's just taking an entire plane and then flipping it around the unit circle, which is slightly strange, but works out okay. And so you end up with this reciprocal region of convergence, that if the region of convergence was everything outside some region, then all those points get flipped inside, so you get everything inside some radius. But that makes sense, because here we're saying, well, a right-sided sequence has a region of convergence that's the exterior of a circle. If we flip it in time, it becomes a left-sided sequence. We expect that thing's region of convergence to be the interior of a circle, and that's what 1 over z does. Time shift. Again, this comes out very simply. If you plug it into the z-transform expression, then you can start separating out. You can do a change of variable to make it, g of n dash, where n dash is n minus n0, and you just get g of z with a z to the minus n0 scaling factor. And so this is, and we notice here that when we're drawing our block diagrams, if we wanted an n0 step delay, the way we draw that is a box with z to the minus n0 in it, because in z-transform space, a delay is just multiplying the z-transform by some power of z, the power corresponding to the number of steps delay. So that's why we use that convention, and that's sort of one of the nice things about the z-transform, that now it turns delay into multiplication. So that other thing we might want to do in our blocks, we can quickly turn into just an algebraic, simple algebraic operation. If we delay something, we don't really expect its convergence properties to change, right? So the region of convergence stays the same. Of course, if we have an expression and we multiply it by some power of z, then if we multiply it by z to the minus 1, and then we try and evaluate it for z equals 0, then we've got a 1 over 0 term in here. So that's like, well, you can't say you can't. If it used to be something you could evaluate at 0, and then you divide it by z, you can no longer evaluate it at z equals 0 if it was a finite thing before. So you might get additional poles coming in, additional regions of non-convergence coming in at z equals 0. And you could say the same thing about z equals infinity. You multiply it by z, and then you evaluate it, and it had some finite value at z equals infinity before, and then you multiply it by z. Now it's going to take on an infinite value at z equals infinity. Convergence means that the value is not infinite. And so if we have some expression, even if it's sort of maybe not so dramatically ill-behaved as the ones we saw in MATLAB, but if it evaluates something that's infinite, then that does not count as convergence. And so that's why the region of convergence can never include these poles, because a closed form expression goes to infinity at a pole. It's got 1 over 0 somewhere in it, which means that, well, that's not converging. So that's always outside the region of convergence. So anyway, the region of convergence may differ in whether it includes 0 or infinity. Of course, we never really see infinity, so it's hard to think about whether it's actually in the region of convergence or not. Technically, these are important. In practice, I typically don't worry about regions of convergence, 0 and infinity. And the thing is that extra roots, extra poles and zeros at 0 don't have an interesting, in particular, they don't affect the Fourier transform, because a pole at 0 sort of has a uniform effect on the values at 1. If you've got this pole at 0, it'll push everything close to 0 up around. But by the time you get to the unit circle, it's balancing out. And so it doesn't affect the Fourier transform magnitude. So again, we'll come back to that, but they're less interesting than other poles and zeros. Z transform of an exponential scaling, alpha to the n, g of n. Again, if you plug this into Z transform expression, you can do a rearrangement, and it's now g of z divided by alpha, which is just saying it's the same surface, same set of values for all values of z, but we've just sort of scaled we've zoomed in the entire z-plane to be larger or smaller by a factor of alpha. And so values that were further out now become the values on the unit circle, or vice versa, depending on the size of alpha. And the region of convergence is similarly scaled by alpha, because all that's happened is we've just redefined, it's like we've relabeled the z-plane axes. Here's one that didn't show up on the DTFT. But if you have this expression, right, you have g of z is equal to the sum of g of n, z to the minus n. If you differentiate it with respect to z, you've got g of n, z to the minus n. So if you differentiate with respect to z, you get minus n g of n, z to the minus n minus 1. Something like that. And so you end up with something that begins to give you the z transform of g of n scaled by n. You need to take out a power of z to make it all work. But basically, this is a way of if you want to know the z transform of this, and you know the z transform of g of n, you can quickly get it by just differentiating that with respect to z. Okay, it's just an algebraic trick that works out. And in general, this will not impact the region of convergence, except possibly at the extremes. Let's just finish these. Let's just finish off these properties. The important DTFT property, of course, was the convolution became multiplication, and it still works here. It's true over the entire z-plane. You obviously, well, if the z transform converges for both G of Z and H of Z for that particular value Z, then the convolution will work as well. It's possible that by convolving them, you actually you will gain extra points where it converges that didn't converge before, although that'll be a very special case. The dual of convolution was modulation, where instead of convolving in the time domain, we multiply in the time domain. In the DTFT, that was kind of nice because it just looked like convolution on the frequency variable. Of course, in the Z domain, there isn't a frequency variable here. This is actually the same thing, but now what it is, it's a contour integral for a closed contour in Z space. And so here's our convolution dummy variable, which is now a second complex variable, and we're integrating for all the values on 1 and then the reciprocal of that. It's the same thing, but it doesn't look really so transparent in Z transform representation. So this gives you, right, a function of Z here. And then Parsifal's relation, which said that the sum of the magnitude squared in the time domain was the sum of the magnitude squared in the frequency domain, generalized to two sequences. That also works here, but again, it has to now be this, the sum over all frequencies becomes a contour integral in the Z plane, and then instead of being a function of Z, it's just a constant function here. But it's basically the same expression, but evaluated for a particular value of Z. These are not payoffs. This stuff is much easier to think about in the Fourier domain, but just to show that it is properly generalized into the Z transform. All right, any questions about that stuff? Okay, so we're sort of you know the basic idea here, and I've told you what the right way, the way I want you to think about it. But we're still going to work through it, and hopefully it'll become more clear and more useful as we go on. See you.